Hello, welcome to our lesson 3.1. So in this chapter, we're going to dive into some functions and graphing and all sort of good stuff like that. But we're going to start with just function notation. So I think a good place to start is, well, what's a function? So we got the textbook definition here, and I want to tear it apart and make sure it makes sense. And we'll use this later in another chapter as well. Okay, so a function is a math relation between inputs and outputs, where each input is related to one and only one output. So in today's lesson, the main part I'm focusing on is that it's just some sort of relation between inputs and outputs. So it relates two things for us. Now I'll go ahead and tell you, when we're doing math in Algebra 1 and dealing with functions, whenever we're thinking of inputs, we're thinking of x values. Okay? And whenever we're thinking of outputs, we're thinking of y values. Okay, x values and y values, inputs and outputs. On our graphs, if you think about, we haven't talked about graphing a whole bunch in 2 dimensions yet, but if you think about a coordinate plane here, or a Cartesian plane, we have two axes. The one that runs left and right is the x-axis, and the one that runs up and down is the y-axis. So if I'm thinking graphically, I'm thinking x values, I'm looking at where the graph is left and right. If I'm thinking y values, I'm looking at where the graph is up or down, or some people think of this as the height. Okay? There's some other words we'll relate later, such as related to, not exactly saying it's the same thing, but it's related. We'll think of domain and ranges, but we'll talk about that later. Now, the special part of the relationship that makes it a function is that each x value is related to one and only one y value. Okay, and we'll dive much deeper into that in a few chapters. For now, I just want you to get this idea that a function is just a way of relating x and y values, but it gets us thinking in this idea of inputs and outputs. We've kind of already have most of the skill to deal with some of this thinking. Okay, now the fancy way that they write functions is just to replace the y's with some fancy notation. So this is the function notation part right here. So if we're looking at this, notice these are exactly the same. They're both 3x plus 2 equals y, which is the output. 3x plus 2 equals this weird notation here, but that is the only difference. And the way we read this is we look at the letter out front and whatever's in here, and we say f of x. So whatever letter of whatever's in there, f of x. And we can have numbers in here and all sort of stuff. Numbers, symbols, whole other functions. So f of x. So this is the same thing as our y. So these are interchangeable. But if I want to use my best proper manners, I would like to use function notation. And then everything else is identical. What's really neat about this is, or let's label some of these pieces and talk about why this is useful at all. So the letter out front, that's the name of our function. So that gives us the ability to have several of these out listed and to be able to tell you which we would like to work with. Also, we already have talked about the input, but I can ask you things like, hey, could you find f of 5? Without having to rewrite the whole problem with a 5 here, I can tell you, and you do all the scratch work, hey, I tell you what function to use, and I'm telling you what I want you to plug into it. Tell me what pops out. Tell me the y value, the output. And so this kind of notation gives us freedom of having multiple functions going on without having to, well, multiple functions going on, and I can have you plug in multiple things without rewriting the problem. Okay? And it's a very succinct notation, and it gives us a nice visual of what's being input. And then whenever we do find the output, let's say we pretended we plugged in 5 and we got the answer was 12. Well, then we know what the input is. That's the piece in there, input. And we know what the output is. That's right there. And so it's a very succinct, very tight writing. Instead of having a whole expression written, I can just easily say, hey, this function, when I plug in 5, spits out a 12. Now, please do not disconnect the ideas that this is just our x value and this is our y value. So this is saying, hey, when we have an x value of 5, this function is equal to a y value of 12. Okay, so this seems weird. It doesn't seem super useful yet, but as you dive deeper and deeper into it, functions provide a lot of good things for us. There's whole courses where they study functions and special things you can do with functions, and you'll dive a lot deeper into functions. We'll even dive deeper into certain types of functions later in this course, but you'll spend a lot of time studying functions in Math 111 when you move up to the next course. Okay, so now here's some examples of some of the things I can do with functions. For just on the simplest introductory level, to use function notation, I can define several functions. So you see my blue writing. Oops, it messed up my, let's fix this. Messed up my exponent when I change colors. There we go. I can define several functions. I could define 10 of these, and then I don't have to write them over to ask you questions. Okay? And you know exactly which one I'm telling you to plug into whenever I tell you the name of it by the letter. And then I can tell you exactly what to plug in, so I don't even have to write a whole lot. So I have 2 functions defined here, and I have 4 questions written, and this takes like half a second to write all these questions. And everybody in here, once you understand function notation, everybody knows exactly what we're talking about. And so, just as a way of example, let's work these out. So alright, so we look at this. The first question is find f of 2. Okay, well, what function am I using f? So that's this one. And what letter am I plugging in? Or sorry, what value am I plugging in? I would like to plug in a 2. So this is how we're going to do this. I know almost everybody here probably can do this without my help, but I'm going to want to set kind of a standard for how we do this. It's going to be really annoying to you, but it will serve a purpose as we progress throughout the course for proper handling of plugging in numbers. I would like you to ignore what we're plugging in for a second and just see what function we're using. We're using the function f. I would like for you to rewrite f except for leave blank parentheses everywhere there's an x. So if I'm writing that, that's negative 2 blank squared. So let me write this out. Negative 2 blank squared plus 3 blank plus 3 blank minus 4. And I'll move this over. I'll move all these over. We'll just grab them whenever we're ready to work them. That way, maybe I can even write this a little bit neater. Okay? So let's see. Negative 2 blank squared plus 3 blank minus 4. Throughout the class, I'll encourage you to do stuff faster and show less steps and take bigger steps as you're able to do them. But this is something I never want to have you drop. I know this is annoying. I know many of you know to put the 2 in there, but I would really like for you to start every time we have to plug in something to rewrite whatever you're plugging into carefully, piece by piece, leaving blanks for the x's. This helps with several bits of understanding and also hugely to help avoid mistakes. All right, now that I've rewritten it with blanks, what am I plugging in? Let's go and look in our function notation here. I'm plugging in a 2. So I can just plop the 2 in there, and now I'm ready to rock and roll and find the value of this. And we would need to be careful and use order of operations or use a scientific calculator. Order of operations tells me I'll do the square first. And so 2 squared would be 4. And then, let's see, negative 2 times 4 is negative 8, plus 3 times 2 is 6, doing order of operations, minus 4. And then negative 8 plus 6 is negative 2, minus 4. Negative 2 minus 4 is negative 6. Okay, that wasn't terribly hard. I'm going to group these together so I can shrink it and take up less space. We'll put it over here. All right, that wasn't too bad. Let's do another one. Okay, let's do one where we have to be more cautious of signs here. So it says, just like I told you last time, if we're going to plug something in, I would like you to start by simply rewriting the function with blanks. Don't even pay attention to what we're plugging in. So the function is minus 2 blank squared plus 3 blank minus 4. And this is one of those big reasons for using parentheses. What am I plugging in here as a negative number? Okay. If you don't have parentheses, you can try this in your calculator. If you drop the parentheses here versus having the parentheses, you will get two different values because your calculator is not smart enough to know that you mean squaring -1. -1 squared is different than -1 in parentheses squared. Because what we need is we need some sort of notation to understand when we want to square all of -1 or when we want to square 1 with a negative floating out front. -1 squared is -1 times -1, which is just +1. -1 squared with no parentheses, even though you probably mean this one, if you type it this way in your calculator, it'll tell you -1, which is like gonna blow some people's minds, but that's okay. That's why I want you to have parentheses, especially if you're going to use a calculator, so that you don't accidentally mess up the signs here. So then I would just need to go about using either a calculator or careful order of operations. -1 squared in parentheses here is going to be a +1. Oops, not equals. All right, so now I can do these multiplications. -2 times 1 is -2. 3 times -1 is -3. Bring down the -4 or -4. -2 plus -3 is -5. And -5 minus 4 is -9. Okay, nice. So this is nothing but arithmetic once you understand how to plug into the function, but it's good practice to practice plugging into these functions and using this technique of rewriting it as blanks where the x's go, rewriting it first before paying attention to what you're plugging in. Let's keep going. We'll do these last two examples. They're really quick and easy. So what function am I using this time? Thank goodness g. It's a less intense function than f. So I'm using g here, and let's get the g function. It's 2 blank plus 7. So 2 blank plus 7. And in that blank, I'm plugging in 2. Okay, well, this is really easy. 2 times 2 is 4. And if I wanted to finish this up, 4 plus 7 is 11. That one was really simple, not super duper involved. Okay, nice. All right, one last one. So one of the huge ideas with functions is if I don't use function notation, I have no way to conceptualize plugging in weird stuff. So sometimes in functions, we want to plug in something other than a number. I might want to plug in some placeholder, some letter that stands for something. Or I might even build up to wanting to plug in another entire function into function. This happens all the times whenever people are doing some real level math and stuff. They have a function that may tell them the temperature. Well, it may tell you the number of ice cream people need to have ready to sell at their ice cream shop because it's based off of temperature. You plug the temperature into that, and then they may not know what the temperature is going to be, but they have a forecast to estimate the temperature. So they may plug in the stuff into the temperature function and then plug that function into the ice cream function. And so like it's a silly example, but there's a lot of things where functions plug into functions. So this is just the very beginnings of us understanding that, hey, I can plug a lot of different things into a function than just numbers. And so I will do it the same way. I will write the function g, ignoring what I'm plugging in, and g is just 2 blank plus 7. And then, now this is going to feel really pointless because this is just an m and it doesn't mean anything to us. But what am I plugging in? I'm plugging in an m. Okay, can I simplify this any? Well, 2 times m is just 2m. And plus 7 is not a like term, so I can't combine them. So that's as far as I can go. So g of m equals 2m plus 7. But that's okay. We're just learning and expanding our abilities. Now, the other important place to go with functions is graphs. Okay? And this is a hugely important idea to be able to connect back and forth between graphs and function notation and x's and y's and coordinates and all that, okay? So one thing I want you to know is that if I ever have a function, whatever I plug in is the x value and whatever it spits out is the y value. So for instance, if I knew a point, let's say I knew that we had the point g of 3 is equal to 1, well then you could tell me the coordinate. that may be a good test question. Hey, if I gave you the function answer, if I told you plug in a 3, it'll spit out a 1, what is the xy pair, the xy coordinate, the point on the graph? Okay, if you don't know this yet, points and coordinates on the graphs are written as x, y pairs like this. Not to be confused with interval notation, which can get confusing, but when we're talking about points, you'll know the kind of the context and you'll be able to tell them apart just from the context of the problem. So I'm asking for a point here. So what coordinate or point would this be? Well, it's really simple. It's just 3, 1, x, y. Oh, okay, that's really easy. We'll ask you, maybe we'll give you on the test a function notation and say, hey, what is the point? What coordinate is this? This coordinate or this point is 0.31. Now, when you have a graph, let's say we have this graph g of x, this also means stuff on the graph. Like, oh, look, I have this point. Remember, these are the x points or coordinates, and this is the y-axis where the up and down movement is your y-coordinate. And so if I go 3 in the x and 1 in the y, this point is on the line on this function. Well, definitely, if it's a true statement from the function, it is a point on the function. Okay, that is a huge understanding to have. You have to have that understanding to move forward with a lot of algebra at higher levels. It's a very basic understanding that a lot of people don't have connected. That if I have any function notation and it's true, then it is representing a point somewhere on this graph. Okay, so I mean, I could do a lot of things. I could give you an x value, like say, hey, find g of 3, and you would just go look for x on the graph and find a point that has an x value of 3, and you could know what the output is. Well, what's the output? What's the y value at this point? It's a 1. Oh my, I could give you I could say find x when this is equal to, we'll just keep using the same point. This is equal to 1. Okay, well, this is the y value, so go on the y-axis and find this height and trace it to the function. Oh my, I know the x value is 3. So we could determine a lot if we have a graph and we have function notation. I can give you an x and you find me a y. I can give you a y and you find me an x. I can ask for a point, a coordinate. I can do so many things. So let's practice some of the skills with a little more intense of a graph. So here's this graph, function h is what I'm calling it. It's a beautiful graph, much more beautiful than when I teach in person, because I usually attempt to draw something like this by hand, and it never goes right. I'm not the best at drawing things. So here's two questions that we might ask. Hey, for what x values does this function h of x equal 1? Okay, so let's think real quick. What are they giving me? Are they giving me the x value? No, they're asking for the x value. They're giving me the y value. So let's go on the y-axis and find a height of 1. Here it is. This is 1. Now, something I wrote earlier, these outputs or y values are the same things as heights. And notice that I hint there could be, not always, but there could be more than one x value that spit out this height of 1. Okay, well, first off, let's just pick off this point. What x value is this? Well, it doesn't move left or right any. It's right on the axis, so it's an x value of 0. So that's one of them, x equals 0. But there happens to be another spot on the graph at the same height, right here. This also has a height of 1, doesn't it? And what's the x value that matches that? Of 4. So this has two answers. X could be 0 or 4. If you wanted an output of 1, I could find you two spots on this graph that give you an output, a height of 1, at x equals 4 and x equals 0. Okay. Some people get confused on this, so I just say it's nice to have all these words to relate things. The y, the height, the output. To be able to interchange these and have true understanding of what a y value of 1 is. There's a y value of 1, so I go on the y-axis to 1 and trace this line. This is the height of 1. It's up 1 from this x-axis. Okay, now let's do the opposite. Hey, could you find the value of h of 3? Huh. Well, this is the x value they're giving me, so I must be looking for the y value. So I have the input, the left and right movement. I need to find the height. So this is function h, so let's go with a 3 in the x value. So here is a 3 right here. Now let's see the height of this thing. Well, there's no graph above it, so it must be below. It must be a negative height. And oh, look, if I trace it to the graph at this height, or this left and right movement, this must be my height right here. And it is a height of -2. So if I plug in a 3, I get -2. Okay, so on this graph, I have this point, 3, -2. All right. That confuses some people, so take some time to think about it and stare at it and kind of ponder it. That is some of the deeper understanding that we've covered. So some of the deepest things I'm asking you to understand. It's very light on the surface, but actually it has a lot of depth and wealth of just good math stuff there. So take some time to make sure you understand that. But that's all I have for you in this lesson. We'll Chapter 3 will be kind of a fun one that's not too challenging, hopefully, as we move on to some graphing next. Okay? All right, well, see you next time.